Good morning, everybody. Uh, this is going to be the notes on Chapter 8, which is all about Earth systems. It's going to get into geology, mining, soil, things like that. We've already talked about some of this, so we're going to go fairly quickly through this first part. We talked about how when the Earth first formed, all of the dust clouds started to collect out in outer space. As that dust cloud collected, we started to have gravity kind of pulling it in towards the center. Once that happened, we started to have our sun form. Once the sun formed, that gas cloud continued to compress and continued to become more dense. It started to spiral around the sun. Then we started to have our large planetary objects start to form. As those planetary objects became more and more dense, then they formed into the true planets that we have today, whether they were the gaseous planets like Jupiter or whether they were the more solid planets like the Earth is. And again, the Earth formed, it was about 4.6 billion years ago that the Earth formed. I forgot to open up one program here, so let me open that up while we're going through this stuff. So again, 4.6 billion years ago is whenever our planet formed. And it formed in a unique kind of way. It formed into different layers based on either composition or based on physical characteristics. If we look just at compositional layers, we just have the core, the mantle, and the crust. Those are the three distinct layers. When we look at the core, we have an interior core that's made mainly of iron and nickel, and an outside core that's kind of molten and surrounds that inner core with it. When we look at the mantle is going to be that magma, the molten rock that the solid crust kind of floats and wiggles upon. When we look at it based on physical characteristics, that's whenever we break it into 5 different layers. So we still have the core. We have an inner and an outer because the inner core is a solid due to the high pressure that's on it. We have the outer core, which is going to be a liquid because it's going to be a molten layer. Because again, the temperature, despite being about, I think last time I read, I think it was like somewhere around 3,000 degrees. The inner core, the iron and nickel, should be liquid at that temperature. But since there's such high pressure on it, that makes it into that solid core. So now instead of just looking at it from a compositional standpoint, we split that core up into 2 different layers. Now, when we look at the mantle, also, we split it up into 2 different layers. We have the mesosphere, which is the magma, the lithosphere, which is sort of like oceanic and continental crust, and then we also have the asthenosphere, kind of in between the 2 of those. All right, now in some places, what we end up with is let me get this set up here better so that I can annotate on here. In some places of the crust, that continental and oceanic crust, in some spots it might have a little bit of a thin spot. So let's say that this is our crust here, and this is going to be the thickness of it. Every once in a while we may have a spot that's a little bit thinner than other spots. That magma underneath now can interact with that thinner spot, and through the little fissures and cracks can kind of peek its way up to the surface and form a volcano. The other way this happens is that if we have superheated magma, we'll make that into this pink color. The superheated magma actually will start to melt that solid crust, and as it melts, it kind of makes it thinner and thinner and thinner until eventually it peaks out and starts to come to the surface. As that comes to the surface, it solidifies and it keeps on building upon itself. And that's how many of our islands are formed, is through those hotspot activities. Now, don't forget, our crust is made up of the tectonic plates. So the entire time this is happening, that plate might be shifting to the right or to the left. So as that's happening, we're talking on geologic time. At one geologic moment, it may be here. Geologic moment might be several 100,000 years, if not a million years. The next geologic moment, now that plate is shifted, it starts then to peak up through here, because now this is the area of the plate that's over top of that hot spot. So that's why we get what's called the island arcs or island chains. And again, we talked about all this in class, so hopefully this makes sense to you. And again, this is just showing those magma plumes coming to the top. That's that superheated magma that's kind of melting and convecting its way up. As it comes up to the surface, that superheated magma is what we call that hot spot. It's melting away the crust, and it's creating these little wee fissures that are peeking towards the top. They're peeking out, they're creating those islands, and then here you can really see that island chain is forming. So again, the direction of this plate would have been so that it went this direction because this was the first spot that it hit. Then a little bit later on, a different location was, underneath that hot spot, and then now it's back here to this spot. So that's eventually, if those would peak out through the water, through the ocean, that would form one of those island arcs or island chains. All right, now we have the plate tectonics. Again, that surface crust, the continental and oceanic crust, that is on top of that asthenosphere, which is kind of like jello. So it's bouncing and wibbling and wobbling back and forth. As it wiggles and wobbles, there's little fractures that happen in that crust, and it's what gives us our tectonic plates. So our crust is not just one contiguous piece of solid material. It's broken up of several different plates. There's 7 major plates and a few different minor plates. So depending on which scientist you talk to, it could be anywhere from 13 to 15 total plates, somewhere around there, depending on which size they differentiate as being a plate or not. And again, those plates are in constant motion. That constant motion is what gives us our geologic features that we have on our planet, whether it's the volcanic chains that are forming our islands, whether it's underwater ridges like we have here. Whether it's the mid-Atlantic ridges like we have here, where it's an underwater ridge formed by oceanic divergence, whether it is more of a mountain range like what we have here, where there's subduction happening, and when that plate subducts under, magma comes up, creates a inland mountain range from the subducting plate, causing more and more magma pressure to form. So we have all different kinds of geologic features that happen at these plate boundaries. Where those plate boundaries occur, we have increased earthquake activity and increased volcanic activity as well. The main area is this ring of fire over here in the Pacific Ocean. So again, where we have the different plate boundaries, we can see subduction happening, where the more dense plate is sliding onto the less dense plate. And you can see it kind of deteriorates and melts into that magma as it goes. As it melts into that magma, it builds up magma pressure, and you can see you end up with like a little bit of a mountain range here. Because again, that magma is building up pressure, it's pushing the crust up, and it's also potentially forming some volcanoes in there. When we have divergent plate boundaries, and we can see that this is oceanic divergence, because we're out here in the middle of the ocean, we end up with seafloor spreading. And basically you have those two plates splitting apart and pulling apart. As they split and pull apart, magma rushes up to fill that gap. As the magma rushes up to fill that gap, it's not just a smooth layer, it's kind of a jagged mountain range that forms. So where we have the seafloor spreading at, we end up with a mid-oceanic ridge. The biggest one, again, is the mid-Atlantic ridge out in the middle of the Atlantic Ocean. Now, we can also have different other types that are forming. This picture doesn't show all of them. It's mainly showing the subduction and the divergence, the convergent plate boundary and the divergent plate boundary. We'll get more into the other ones. Subduction, again, that's the process where the more dense plate, when those two plates are moving in towards one another, where there's two bits of the crust kind of moving in. Let's say this is our more dense plate. What's going to happen is that more dense plate is going to kind of start pushing underneath the less dense plate. And what you end up with is you have a trench that forms right here, where there's that little bit of a gap, and then as this plate moves further and further down in, it starts to melt. As it melts, it builds up magma pressure, kind of pushing up on this plate, kind of creating like a little bulge or a mountain. And then if there is volcanoes, that's whenever you get the larger mountain ranges that form. All right, one of the biggest things that we see because of this plate movement, we had a hot spot out in the middle of the Pacific Ocean. So this little yellow dot, everywhere where you see a yellow dot, that's saying where the hot spot was at. The hot spot is located right here. It's in a fixed position, right? That hot spot does not move. However, the plate that that hot spot is over top of does move. So in this case, it's moving at a direction that goes like this. So when we look at where this hot spot used to be at, originally, when the island started to form, when the hot spot became active, the plate was over top of this spot. So, if we trace back 5 million years, we would see that the plate had moved that much over those 5 million years. So 5 million years ago, we had the hot spot, located over this piece of plate. underneath this piece of plate, I should say. So that hotspot was here, it was bringing magma up to the surface, and it ended up forming the island of Kauai. All right, I can't pronounce the other island that is over here, but the Niihau, or however you say it, that's going to be another one of the islands that was over there. Again, about 5 million years ago. Then it kind of took a little bit of a break. The hotspot was not active. The crust might have been a little bit thicker, might have been a little bit more dense, so that magma wasn't able to get to the surface anymore. Once it started to go to the surface again, we had two different locations over that. What is it? From 3.7 million years ago to 2.6. So we're looking at almost a million years. We're looking at 900,000 years that it took to form Oahu. And again, we had the first part of the island that formed, and then that plate was moving that whole time that it was forming, kind of creating more and more crust, more and more of an island. So you can see that you end up with these island arcs because that plate is constantly moving the whole time that hot spot is turning magma up to the surface. All right, now there's going to be three different types of plate boundaries. We have a divergent boundary, divergent meaning they're going to be moving away from one another. So they're moving in opposite directions. At divergent boundaries, we have seafloor spreading that occurs. That seafloor spreading, again, that's when the plates pull apart, the magma comes up to the surface, and it ends up forming, if it's two oceanic plates, it ends up forming an underwater mountain ridge. Because as those plates pull apart, that magma is coming up, that kind of jiggly magma comes up to the surface, and there's enough pressure that it pushes way upward, creating the mountain ranges. Oh, hold on, the lights just went out. Sorry, the lights are on the automatic timers. So when we look at the seafloor spreading, we have new seafloor forming anywhere where there's a divergent plate boundary. All right, convergent plate boundaries, that's going to be where they start coming in, moving in closer to one another and coming in direct contact, kind of pushing into one. This is where it's a little bit different based on what type of plates you have. If you have two dissimilar plates, an oceanic plate and a continental plate, the oceanic plate is going to be more dense than the continental, and we're going to have the oceanic subducting under the continental, because the more dense plate always subducts under the less dense. So we have the continental here. Again, we get a valley where the plate boundary is at, and we get usually a mountain range in interior on that continental plate. Whether it's through volcanoes or whether it's just through that magma pressure as that oceanic plate melts, pushing up to the surface. If we have oceanic convergence, then we still have the same process happening. It just has to determine which one's more dense. There's going to be a slight density difference here. So whichever one of the two plates is more dense, let's say that this one here is the more dense plate, we would have subduction happening still with that. So again, anywhere where you see convergent plate boundaries, and it's oceanic plates involved, whether it's an oceanic and a continental or two oceanic, you're going to have subduction happening. If you have convergence with two continental plates, now we have very low density plates here. When you have two continental plates converging, that's where they're going to kind of crush into one another and form that terrestrial mountain range. Again, terrestrial being land-based. The Himalayan mountains were an example of this. We have those two continental plates slamming in together, pushing up the material and creating those, rather tall mountain ranges like the continental plates are. All right, third example, transform. This is where we have plates moving in I don't want to say equal, in opposite parallel directions, I should say. So we have one moving, upwards, the other one moving downwards, perspectively speaking. They're not going to be moving up and down like this. They're going to be moving side by side. They're going to be parallel but opposite directions. The biggest example of this is the San Andreas Fault out in California. So again, we see divergent boundaries, seafloor spreading, magma coming up to the surface to fill in that gap. We get an underwater ridge. If it's divergent with two continental plates where it's on land, now we're going to have that area spreading apart. Instead of forming seafloor, it's going to form new land. So if it was two continental plates, now that area in between the two plates kind of keeps on stretching out, and we end up with a thinner bit of crust there, and we get what's called a rift valley. Most of the time, these rift valleys form fairly close to the oceans, so they end up filling in with water, because the water that ends up going below sea level and that water ends up filling in, and we end up with those rift valleys that are filled in with water if it's two continental plates. All right, now these are all the geologic features that are going to form. So in that lab that we did in class, you should have these geologic features filled into your uh, chart. I'm sorry. So if you have divergent boundaries, and we see this divergence happening with oceanic, that's where we get these seafloor spreading and the oceanic ridges. And again, we've covered enough about how that happens. With hotspots, you end up with island arcs. This wasn't in the lab, but we talked about this through the notes here. You also get these island arcs where we have subduction happening. And again, in this case, this would be two oceanic plates subducting. We would have the oceanic, more dense oceanic plate going down under, melting, creating more and more magma pressure coming up. We get those stratovolcanoes that form the volcanoes that we most commonly see, where you have that really defined volcanic shape. Those stratovolcanoes, again, that plate's moving that entire time, so that subduction is going to be occurring as that plate is moving, away from, in a different direction than where the subduction is happening, and you end up with those potch marks of volcanic islands that are out there. Sorry, give me 1 second to get things situated on my screen. All right, now, when we have that happening with a continental plate and an oceanic plate, now we have the subducting plate, but now when we have the subduction melting that oceanic plate, we have a mountain range form that is on land. So, oceanic, we end up with the island arcs. Oceanic continental, we get into those coastal mountain ranges that form. And again, divergent with two coastal, we end up with the Rift Valley. So hopefully that will help you guys remember. Make sure you guys know these different geologic features. There was a question on the AP exam a few years back that they asked about the different plate boundaries and what forms from them. Right? At those transform boundaries, this is where we're going to end up with fault lines happening. And fault lines are just basically big cracks and scars in the Earth's crust, because you have the two plates moving in equal and opposite directions. Even though you can't see my hands, I'm trying to push my right hand forward, pull my left hand back. All right, every once in a while they're slipping, and as they slip, that's going to crack the land surface. So those faults are going to be big fractures in the rock in the Earth's crust caused by movements of those plates. Anytime you have that happening, you're going to have seismic activity, and seismic activity is what causes the earthquakes to happen. And again, when you get really, really big fault lines, you can actually see them from above. Again, this is the San Andreas Fault out in California. You can actually see that it's a pretty big scar to it, and you can see where they've kind of moved back and forth so much that the plates are actually starting to separate a little bit. And this is kind of the reason why you hear all the time that California, we're going to end up with part of it out in the middle of the Pacific Ocean in the future, because it's going to break off of the mainland United States. And it's going to break off, they think, where, with the people that believe that it's going to break off, they think it's going to break off at that San Andreas Fault. Oops. Now, when we look at earthquakes are pretty important as far as the AP exam goes too. The power of them is going to be measured with the Richter scale. There was a guy named Richter. He was the one that developed it. It's a logarithmic scale. So each number on the Richter scale represents a factor of 10 times greater energy than the previous number. So when we have earthquakes around here that are 3s or 4s, those aren't very much power to them. It's going to shake the ground, you're going to feel them, but it's not really going to do too much building damage. Once you get into the 4s, that's where building damage starts, but it's only the basic building damage. We experience building damage because our buildings aren't built to withstand earthquakes. In California, a 4 would hardly do any damage at all. It might break some windows, crack plaster, but it's not going to do any major building damage or any road damage, because they have different standards for their buildings. Just like Florida builds to withstand hurricanes, we build to withstand snowfall on our roofs. They're going to build in the earthquake zones to withstand the earthquakes. So when we look at 3 to 4, though, that's representing 10 times the power behind it. If we compare a 3 to a 5, that's going to be 100 times the power now, because each time you go up is a multiple of 10. So when we look in California, with an earthquake of 6 that does some pretty major damage. And then we have one like happened in Haiti that was up to the 8s. You know, that's going to be 100 times more powerful than what those damaging earthquakes are that happened in California. California experiences mainly 6s and 7s. The one that hit Haiti was a mid 8 to high 8. So we're looking at 100 times, if not close to 1,000 times more powerful now. So that Richter scale is really, really important to know just how much shaking occurred along the Earth's ground. When we look at where the earthquake happens at, most of the time they're going to happen out at sea, or they're going to happen deep underground. They very seldom happen right at the surface. So the area where it happens underground, that's the focus of the quake. I know this isn't on your note page, but make sure you guys know that. The focus is the origination point. All right. Above the origination point on land, directly above it, is the epicenter. They use the epicenters because they need to have a geographic location point in order for people to understand where the earthquake occurred. So if we simply say that it happened 200 miles below ground, that doesn't tell us anything. But if we say the epicenter was 13 miles outside of Pittsburgh, now we know where exactly that earthquake existed. It could be 200 miles below the ground, outside of 13 miles outside of Pittsburgh, but it's going to be 13 miles outside of Pittsburgh so people understand where it's at. We can then see, you know, because those shock waves are going to go out in concentric circles from that epicenter, we can then see how far away is going to be affected, what major cities were in its path. So again, focal point is going to be the area underground. The epicenter is the place on the surface directly above that focal point. And again, if we look at where the earthquake zones are at, it's everywhere that's highlighted here. And again, those earthquake zones go hand in hand with plate boundaries. We can see, just like the volcanic activity, the Ring of Fire is one of our big earthquake zones. But again, we have a majorly active earthquake zone down here in the Caribbean, where we have the Caribbean plate in contact with the Atlantic plate. We have a lot of different earthquake zones across the planet. And again, the more time that is spent not moving, the more the energy is building up. So if there's transform faults, the more time it takes for my hands to move, the more power builds up, the more energy is released, the higher the score on the Richter scale. All right, we're going to stop this video here, and I'm going to do a second video on the rock cycle in just a moment.